Hi, buddy. So welcome to this class on automated planning. This is an introduction which comes without any prerequisites. That means even if you don't know anything about AI planning so far, this is still for you. So you can still follow everything. Furthermore, it is a hands-on introduction, which means that you will actually have to do something. More precisely, you're going to model a planning problem later on with an online editor. So you only need to have a browser at hand. So we start with a basic definition or an intuition of the definition. A classical planning problem consists of three major ingredients. One is the initial state, which lists all the world properties which are initially true. The second ingredient are a set of available actions. And an action, as the name says, is an action, i.e. something you actually do. And what an action does is to transform one world state into a successor world state, so into another one. Well, and the world changes just because you have done something. You've changed the world due to the execution of an action. And the goal is to satisfy all properties listed in the goal description, i.e. what you would like to do is to transform the given initial start state into any state in which all your desired goals are true. And you're turning this initial state into a goal state by finding a sequence of actions. And so at the end, because you've executed your very last action, you have transformed your initial state into a desired one. This is illustrated here, where on the very left, this is the vertical bar. This is supposed to denote the initial state. The vertical bar at the very right is supposed to denote a goal state, i.e. any state in which all the goal properties are true. And in the middle, those dots are initial states. So I could have also drawn the end state as a dot and the start state as a dot. It's really just a convention, doesn't really matter. So all the dots are states. And then you have these actions in the middle. So in this case, this plan that you see here consists of 6 actions that have been executed here. And they have executed a whole bunch of intermediate states. And at the very end, this plan has generated a goal state in which all your properties of G have been made true. Now let's take a look at a few examples. This is the Sokoban game. And on the left, you see an initial state with initial positions for the boxes and for your agent. And on the right, you'll see a goal state. Actually, you see even more than a goal state, because the goal state wouldn't list the position of the agent. That's not required. The only thing you want to have satisfied is that every single dot has a box on top of it. And you can see that this is a goal state, well, because it has all ingredients, right? You have an initial state, you have a goal state, and you have a bunch of actions. So what are the actions here? These are basically the 4 movements for the agent: go to the left, go to the right, go up, and go down. And then you have a plan of a very large sequence of these left, right, up, down actions, which will then lead from the left initial state into the goal state that you see on the right. This here is another example. You have a few seconds to guess what picture that is. In this game, which is called sliding tile puzzle, you have to move these tiles into empty spaces. So after you've done this first action, you can either move this down or this one to the left. I don't see it well, here to the left. And by means of these many actions that you have available, you can turn it into a picture that is already given. So this here would be your goal. So in this case, the goal is actually given. So if you model that, you do know how the goal picture looks like. What you're aiming for, your actual goal, is the plan, right? So the sequence of actions that you're executing, this is what you're really looking for. This is a more real-life application of planning, namely the control of robots. In this case, you see, I think, 2 different robots on Mars. So these are 2 Mars rovers, and they were controlled somehow by planning technology, but not fully autonomously. But there was a system called MapGen, which could create plans automatically, but did then enable the ground control team, if it's called that way, I'm not sure, to make changes to that plan. So both of these texts are given from the NASA webpage. Let me just read the bottom one. The paradigm is to enable the person using the software to critique a plan that the system automatically produces and ensure that resulting plans are viable within mission and flight rules. Right, so this is the job of Mapkin or Mapchen, I don't know, to change plans according to other constraints and to make sure that they actually work for the goal that you currently have. And then, then they're uploaded and executed by the robot. This is another real-world example, which is on a greenhouse, i.e. An automated factory. So on the right, you see these vertical conveyor belts. So all these belts here are the horizontal ones over here. And what you see on the left, that is this eye here, which is an imaging chamber. So the goal here is to move the plants through the imaging chamber, and then depending on what the sensors in this chamber detect, you decide what happens with the plant next, right? Whether it can be sold, whether it needs more light, more water, and so on. And this is an optimization problem, because you're always only controlling one of these 6 different conveyor belts, but every single action, like move to the right, move to the left, also has impact on multiple plants, not just one. And yeah, you just want to achieve your goal as quickly as possible, that all the plants go through the chamber. You might notice here that this is actually not a classical. You don't actually know that yet. You don't know yet the definition of a classical planning problem exactly. Okay, so we will come back to this later. It's also important that planning is domain independent. What that means is that you don't have specialized software or anything specific to the current application at hand, but you always model the descriptions and the actions in a fully general way, which means that you have a general description language, and in this general description language, you're writing the model, which just happens to describe a concrete application. But the entire technology which is involved is completely general. Here you see one example, here. So this here is a fragment of a description language that you will also model with later in this lecture, namely here for Bloxworld. And the language is called PDDL, which is short for Planning Domain Description Language. And this action here is a durative action. In this example here, there's actually time involved. You will not later deal with time, but in this example, this is present. And this is controlling a satellite, and it tells the satellite in which direction to move. So from which direction into which direction, and how much time it needs. And then you see certain constraints, like where is it pointing at the beginning? Where is it pointing during the entire execution of the action, and then what's going to happen as a consequence of performing this action, like what happens at the beginning and what happens at the end. But you don't really have to understand that fully. We're going there. This is really just to emphasize that it's domain independent, and you have such a general description language, and then no matter which problem you have, you're describing it in that language. So there are both advantages and disadvantages of domain independence, and we will here first start with the advantages. So one advantage is that you can use standard solvers. So if you have, like, let's assume you should solve the problem of this greenhouse domain. If you would write new software, then, well, you had to write that new software. But if you're modeling this as a planning task, you can use a planning system. Which already exists. You only have to come up with a model. And this is, of course, cost effective because you don't have to think about and implement that new software. You can just use existing one. And this is also not just cost effective because you're saving time and, well, money, obviously, but it might also have less bugs because the software is older, right? It has already been tested for a while. You also can get optimality guarantees because there's research involved that shows you under which circumstances solutions are going to be optimal, i.e. there cannot be a cheaper solution. And then there's a whole lot of other planning technology. For example, you can check the model for mistakes automatically. You will actually see that because you're going to model a problem later. There are techniques which prove the unsolvability of a task, because not every single planning problem has a solution. Sometimes you're asked or describing a planning problem, and maybe there is no plan, right? No matter what you do, you cannot solve it. And then there's technology that can prove that there's no solution, and it can explain why there's no solution. Speaking of which, you can explain solutions, like you could say why a certain action has to be executed. And you can also verify the correctness of solutions. So if a system produces a plan, then you can give this plan to another piece of software, and that software will verify whether that plan is indeed a solution or not, because the software could be faulty. And there's probably much more that I've missed. So these are just some of the benefits of this domain independence of using AI technology, or planning technology to be more precise. There are also disadvantages. One is that, well, you need a planning expert in order to do planning, clearly, because you have to produce the model. However, I am going to try to turn you into planning experts in just 60 to at most 90 minutes. So it's still much cheaper than using your own software. And furthermore, it's potentially inefficient because whenever you're writing software which is specifically tailored to one and only one example application, then clearly this has the potential of being much more efficient than a software that is completely general. What, for example, a chess computer is so much quicker in playing chess than a general software. Although the example might actually not be the very best because computers are already so quick that you don't need a specialized hardware like Deep Blue that can only play chess. But in principle, that's the case. If you have software or even hardware that's only doing one job, then of course that can be quicker than a general hardware or software. But here I also would like to emphasize the potential because there are some really strong domain-independent heuristics and technologies to solve planning problems quickly. So it might even be that modeling something as a planning task might be quicker, just because there are already so many techniques that ensure the quick solving of a problem. And if you make a specialized approach, then you first have to come up with a strategy, and maybe you don't find the best one. Okay, let's now start with some actual definitions. So you remember that we have these three ingredients: the start state, the goal description, and all the actions that you have available. And now we are looking a little bit in more detail how this world looks like that we can describe by such problems. One is that it's discrete, which means that all actions impose instantaneous state changes. So here, this is an action, that's action A3. Then there's no time in between. But if this here Si is S0, this is S1, this is S2, and this is S3, then there's no time between S2 and S3. But we have the state S2, we execute action A3, and then this instantaneously turns S2 into S3. And this also means there is no thing like a pouring action, right? Where you have maybe a bottle or a tank which is full of a liquid, and you're pouring it over time, but all the properties are discrete, like the tank is full or empty, or maybe half full or half empty, or you could also say 20%, 40%, and so on, but these would still be propositional Boolean state variables. It's fully deterministic, which means there is no uncertainty in the action outcomes. When you execute an action, you know what's going to happen. There's no dice roll or anything, but whenever you execute an action, you know what's happening. It's also fully observable, i.e. there is no hidden or unknown information. You see always everything. And it's single agent, which means like in the puzzle game, for example, you are in control of the actions. What happens when there is no environment or other player. So now we see the formal problem definition, in which planning problems or classical planning problems are four tuples. And yeah, we first look at the first entry, which is V, which is the state variables. These state variables are sometimes also called facts, here, F for facts. It's the same thing. It's really just another expression. What is in the middle here are example states. So you see a crane in the middle, two locations, on the left location 1, on the right location 2. You see a truck that can navigate between the two locations, and you see this package. The package can be in the location, it can be in the truck, or it can be in the crane. And if you think of this world here that you want to model, and you think about what properties, and I have just mentioned a few of them, do exist, and how could you model them, then all these properties, those are your state variables. And in this example, there are only 5 state variables. And with these 5 state variables, you can model all these states that you see here. Let's take a look at the first. The first state says that crate is at location 1. You see, for example, that there's no crate at location 2. And that's simply the case because the crane always points to the left, right? It cannot turn to the right and put it down, at least not in this world, because it's a simple example. In a real world, that might be the case. But here, it's sufficient to have the property crate at location 1. The crate can, however, not only be at location 1, it can only also be in the crane. So this is the second property, or it could be in the truck. And this describes all the possible properties for the crate. And then the only thing we have left is the truck. And the truck has 2 positions. It can be at location 1 or location 2. And this is shown by these 2 state variables here. And as I have just said, states are then describing or are being described by collections of state variables. So if you take a look at the first state as 0, which is, by the way, or which is going to be also our initial state as I, right here, as I, this is as 0. In our example, you can choose any state that you want as initial state, obviously. You are in control of defining the planning problem, but in this example here, it's as 0. Anyway, so if you see the state on the left, then this would be described formally with this set. It's true that the crate is at location 1, and it's true that the truck is at location 2. And this fully describes the state. We call states with the semantic that we are going to use, that they implement the so-called closed world assumption. Closed world assumption means that everything that's listed in the state is true. So here you see that we have the variable truck at log 2 here, and this is part of S0. And that means that this is true because it's being listed, duh, obviously, right? That's why you put it in. But what the closed world assumption now means is that everything that's not listed is regarded false. So for example, you see that the property crate in crane is not part of S0, and that means that this is regarded false. And this is in contrast to the so-called open world assumption, in which the truth value would be unknown, right? So in the open world assumption, you would say everything that's in the state, we know it's true, and everything that's not in the state, we would regard unknown. But in classical planning, we do assume full observability, and therefore we always know in which state we are in. And so there's no unknown knowledge. There's just a bit more of convention. So S is 2 to the power of V, which is the state space. And the state space is simply the set of all existing states. In case you don't know this annotation, 2 to the power of v, that is called the power set. And that is simply the set of all the subsets of v. So for example, if v would be A, B, C, then here we would have 8 elements. We'd have nothing. We would have A, we would have B, we would have C, and then all the combinations. We would have A, B, and so on. So all combinations with 2. And of course, A, B, C would also be in there. Which would be 8 elements. Okay, so it's just a short notation for the set of all states that exist. Second ingredient are the actions. Now the actions are a member of this. In case you're not familiar with this Cartesian product notation, you know already what 2 to the power of v means. And this Cartesian product just means take any element here and put it together to a tuple. So an action here is a 4 tuple. Let's start with the easiest one. C, that's just a cost value. It's just how expensive is the action to execute. And now the first 3 entries are the precondition, add list, and delete list. And they are just subsets of v. This is what this Cartesian product here means. So pre is a subset of v, add is also a subset of v, and del is also a subset of v. You will see examples of this in a minute. Actually, you see already some action names below, and now we will see how these actions could be formalized in terms of such classical actions. Let's start with the take action. Let's see a few examples. So here we have a take action, and here we also have a take action. So what does it do? If you look at the pictures, well, it takes a package from the ground and puts it into the crane, or I think I called it crate earlier. And now you need to think about when is this action applicable? What does have to be true in order for such an action to be applicable? I just said that what it does is to take a crate from the ground, from location 1. But therefore, you can only execute that action if such a crate is actually there. And so we have the precondition, that's why it's called pre, that the crate is at location 1. And now what happens if we execute that action? There are 2 things. First of all, it will not be at the ground anymore. That's why we are deleting that fact. So crate at location 1 is going to be deleted from the state, and it's being added into the state. I mean, not that, but what is being added is that the crate is in the crane, right? Because this gets true as a consequence of executing the action. And to take a look at a second example, the put action, we see this here, and we see that here. So what happens with put? With put, we have a package in the crane and put it on the ground. And well, here the same. We have it in the crane and put it into the ground. So which precondition does that action have? The crate must be in the crane, right? That's the precondition for the action to be executable. And well, because it will not be in the crane anymore, we will delete this. And what else is going to become true instead? It will be true that the crate will be at location 1. So this is going to be added to any state. I also would like to say that in this example here, the preconditions add list and delete list all have a cardinality of 1, i.e. They all talk about just a single proposition. This is just a special case because this example is so easy. There can be much more. Here's a second example where we have different move actions, move left and move right. So if you take one example here only, you see that the truck it actually moves to the right, which might be counterintuitive because the arrow points to the left. But you see that the drug actually moves to the right, from this node to this node, from the node S2 to S0. So what's the precondition to move to the right? Well, it needs to be at location 1, and then it's at location 2 instead, and it's not anymore at location 1. Always the same. And here are the other actions. Now, finally, we have the initial state and the goal state. The initial state is, well, just any state, right? You can just say what your initial state is. In our example, this is supposed to be the initial state. And the goal description is a subset of the state variables. And in this example here, I think it's S5, which is the goal state. Although here we have yet another special case. So in this case, the goal description G, which is this, is completely identical to the entire goal state, i.e., the entire state that you see here is a goal state, which means that we have specified the entire goal state. However, you could also imagine in a bigger example that there's maybe a third location, log 3, and that there is another package laying on this location. And then the goal description would not have to specify whether a package is at location 3 or maybe the direction into which the crane points or whatever. But the goal description really just gives a list of some state variables, and every single state in which all these state variables are true would be considered a goal. It's just in this example, because it's so very, very small, that our goal description coincides with a complete state description. But in general, this does not have to be the case. Okay, we need more definitions. We need a formal definition of when actions are applicable. And if we have an action A, then we can say that action A is applicable in a state S if the precondition is part of S. Okay, so the state S needs to be a superset of the precondition. And if that is the case, so if it's true, if we know that the action is applicable in a state, then the execution of an action generates a goal state. You know already what happens because we've done that in this example. And what happens is that we take the state that we had in which we execute the action, and then we remove here this here is called I'm not sure how it's called. It's a set operator. It removes stuff from a set. So this removes all the elements from the delete list of the set S, and then we are adding the entire add list. And then we can also define a function, which is the state. Well, actually, this is the state transition function. Here we've just defined it. And so it takes an action, it takes state, and it maps it to the successor state. And that function is called the state transition function. And yeah, let's now again take a look at an example that you already took a look at, only that now we're doing it a little bit more formally. So this action is applicable in this state. Why? Because we have this create at log 1, and this is a subset of the current state, which means that everything that we require in the precondition is true in the given state. So it is executable. And it's resulting into that state. And why is that the case? Well, because we are deleting this from our state. So we're deleting that. It's gone now. And we are adding create in crane. So if you take create at log 2 and we add create in crane, well, then we get exactly this. Here I won't spend much time on this. It looks a bit complicated, but all that this does is to extend the definition of action no, it extends this. It extends the definition of action applicability in a single state to action applicability of an action sequence in a state. Right? And it's exactly how you would imagining it, that this sequence of actions is applicable in some state if every action is applicable in the state before that. So I will not go into detail of this. You can look it up in the slides later on if you're interested, because it's literally just saying you have a state, you have an action that produces a new state, and therefore this new action here has to be applicable in that state and generates a new one, and so on. Yeah, and finally, since gamma was defined on a single action, we can extend gamma to work on a sequence of actions. Finally, what is a solution to a planning problem? A solution is an action sequence, which can have either 0 actions or more, i.e. you could have a planning problem in which your initial state is already a goal state, and then the the empty action sequence would already be a solution, therefore we need the 0. But normally, obviously, you will have long plans, not just empty plans. And such an action sequence, a bar, is called a solution. First of all, if it's applicable in the initial state, i.e. every single action is executable in the state prior to it, and it must lead into the goal state, i.e. if you apply the action sequence into the initial state, you generate some state, and that state must be a superset of all your goals. And in this example here, recall that this is Si, and this is our goal description here, which is satisfied by S5. So we can find a solution by first executing this take, then move left, then load, and then move right. That would be a plan. Okay, so yeah, this is pretty much already it. This is the entire definition of a classical planning problem. And yeah, the most important part is, of course, what a plan is. So what's a solution, which bases upon the definition of when actions are executable. Okay, you can't ask questions because this is recording, so I will just continue. We will now take a look at state transition systems. So a state transition system is basically the underlying semantics of a classical planning problem. They show explicitly all states and how they can be traversed by the actions. And the reason why we introduce them formally is because I would like you not only to understand planning, but I would like you to get an understanding on the complexity of planning, like how hard is it to solve planning problems. So informally, a state transition system is simply a graph consisting of states and labeled actions, and where the edges are labeled with actions. And we have a designated initial state that was in our example, it was this, and we have a goal state in our example that was this. And so you have seen all that before, and that is just a state transition system. I just didn't tell you. So you might think, okay, but how is this new then? Well, I didn't define yet what a state transition system is. I've just used it. What I have defined was the planning problem. But the planning problem was a 4-tuple, right? We only had actions. We didn't even have states, actually. The states were produced by actions, but states were not part of the problem. The problem had state variables, which are a compact representation. So this here is the formal definition of a state transition system. I don't want to talk too long about it because it's literally just a mathematical definition of such graphs as you have just seen them, right? So we have a set of states. We have the labels, which are basically our actions. We have costs for labels. We have the transition relation. Those are exactly the edges in the graph. So these are literally edges. We have the initial state and we have a set of goal states. So now what's the difference to planning? I've actually accidentally already given the answer. Classical planning problem is a compact representation of a state transition function, right? Remember, this is a planning problem. And this graph here, you can build that graph from this, but it's not given explicitly as an input. What's given to you explicitly, that's the planning problem. And you can generate the graph from that. And now consider finally an example that you will work with soon, and that is the so-called blocks world. In blocks world, you have various towers, like you see on the left, and you have a gripper. So this is the gripper, and you have let me see which actions you have exactly. Yeah, so you have exactly 2 actions. You can always take a topmost block. So you couldn't take the red block, of course, right? I mean, the gripper isn't that fancy. It cannot do that. So it can only take this block, or it can take this block, i.e. the topmost one. And the gripper is so quick that whenever it grabs something, it also places it somewhere else again. That's part of the action. So you have to specify the block that you take, and you have to specify the goal where you take it to. And you can either put a block onto the table or onto another block. This is how blocks world works. And now let's take a look at the state space. Let's take a look at how large state transition systems are. With one block, there's just one state, right? I mean, that I hope that's completely obvious. Because, well, there's just one situation. It can only be on the table. There's nothing else. If you have 2 blocks, then there are already 3 states. Why is that? Well, if you have 2 blocks, it can be like this. It can be like this. And it can be like this. And now with 3 blocks, I'm already not going to write that down even because it's so many. So with 3, we already have 13. With 4, we have 73. With 5, I think we have 501, 503, yeah, 501. And then it continues to explode like this. And if you look at this number, I don't even know how to call that number because it's so large. Right? And this is just 18 blocks. That's nothing. I mean, even this is already 5. So it's just a bit more than 3 times as many blocks. It's literally nothing. And now look at all the number of states that you can produce. That's a huge number. So I would like you to give an intuition of how many states you can explore even in very, very easy appearing planning problems. Oh, by the way, you might wonder, why is this even a planning problem? Well, it's not yet a planning problem, but you can turn a planning problem out of it by asking to produce just one tower with a certain arrangement of these blocks, right? So you have an initial situation and a goal situation. And then again, your problem solver, your planning system would then navigate the gripper and tell which block to take and where to put it. Okay, so the main message why I showed you this is that with planning problems, we can obtain a much more complete representation than with state transition systems. And that is because with just n blocks, with 5 blocks, for example, there's already a state space of 501 states. But if I would ask you to write down such a planning problem, then you wouldn't need 500 lines or whatever, right? It wouldn't be that large. You wouldn't draw a graph with 500 states. You would only draw a few actions. How many actions? You're actually going to see in the next part, which is the hands-on part. So now, oh, I was too quick. But yeah, it's actually just saying what I was just saying. You will model this with PDDL. You've seen that already with this derivative action in PDDL that tells the satellite in which direction to navigate. And now you're doing this with blocks world. So you're going to model that, and you will see that even with 5 blocks, you're not going to need hours and hours to write 501 states. You're going to do this much more compactly with just a very few actions. Okay, let's assume we do now have these 5 blocks, and we give them a name so that I don't have to know which colors these are. And they're called A, B, C, D, E. Now, however, we change the action model a little bit. It gets easier to model that way. Although the state transition system will actually even grow by this, but that's not really a problem. Okay, now we have different actions. Now we have, now the gripper can take a topmost block, and as a consequence, the block will be in the gripper. And then we have a separate extra action to put it down again. And if we put it down, we can either put it on the table or we can put it on another block. And this is different from before, because before we could, whenever we put the block, whenever we took a block, we were putting it directly somewhere else. It was one action. And so in terms of the state space, blocks could never have been in the table. No, sorry. They could never have been in the gripper. But in this model here, because we have an action to grab it and also an action to put it down, the gripper will actually hold a block also during a state. So the state space will be larger that way. But again, that's not a problem. And now the question is how we model that. And so we need to see which properties we need, just like in this other example with the crane, right? You need to specify which properties we need. Since the gripper can only take a block which is very at the top, we need to know which one's at the top. So we have these properties: A is topmost, B is topmost, C is topmost, and so on. Then we can ask for that in the precondition of an action. We will also have to know on which block another is laying. And the reason is so that we can specify which block will then be the next one, which is on top. So for example, if the gripper here takes block A, which will mean that the A will then be in the gripper, then B will be the topmost. But we need to encode this into the action. And because of this, we're encoding that A is on B and A is on C, and so on. Don't forget, here I'm just listing all the variables. So in this example that you see over here, A is not on C, A is on B, and B is on C. But this is a state variable which exists in the model. Well, then we also have to say what exists on the table. So A is on the table, B is on the table, and so on. We need to specify which block is in the gripper. This is done with holding. And we also need a variable to specify whether the gripper is free or not. And now we are going to model that we put one block on top of another. So let's say we have block A in the gripper. Just assume that A is in the gripper already. And we want now to put it on top of another block. Which other blocks exist? Well, it's B, C, D, E. So we need 4 more actions, right? So for every other block, we need to specify 1 more action. And you now do this by opening an online editor. And you will work on a model which I have already prepared, which you can download from my webpage, where which is available under this tinyURL here. And since this is a pre-recording, you can stop the video any second from now and just follow this. I will just continue to blabber for like 5 or 10 seconds. Oh, and I will actually also show very quickly how this editor looks like. But I would recommend to you, to please do this at home anyway. So yeah, this is the online editor, and you will you can just select the file from that zip that I've made available online, and you will get this domain file over here where a lot is already provided. And then you find this exercise 1 where you're being asked to complete this model here. So this is what you will have to do to complete this very first action. And here you see some of the predicates which I have already provided. Okay, going to continue now. So I would, if you're really a beginner with planning, I would recommend you to do this now, and then I show you the solution. Okay, so I will continue now, but I hope that you have done this by yourself. So this is the solution. We have to hold block A in the gripper, right? This was our assumption. And if we are putting it on B, then B is the topmost. And now what happens if we execute that action? It's not true that we are holding A anymore. And it's also, no, but now it has become true that the gripper is free because we've put the block A away, right? So now the gripper is free. Also, A is now on B and A is topmost. And because we've put something on the block B, B is not topmost anymore. If you didn't get that right, then you see that it's very easy to forget something. So modeling can be quite a tedious task because you just have to have your model in mind and to make sure that you're not forgetting anything. And now as a second exercise, we are going to model the removal of a block from another. So now assume that we have a B and A is on the B, or in a different world, we would have a C and A is on top of a C, and we always take the A down from that other block. So we would have to do that for all these 4 blocks. But in this example, you're only doing it for one single case, namely for B. Again, I'm just showing the exercise. You just have to scroll down a bit, where again, exercise 2 now says that this is the action that you should complete. And again, for your convenience, I have copied all the available state variables over here. So again, I will not give you time because you can just stop the video. So please pause and do this exercise now. I will directly continue to show the solution. Okay, so to unstack A from B, i.e., as I have just said, we have multiple blocks, but one of them, or the most important thing, is that A is on top of B. So in order to be able to take A down from block B, A must be on B, A must be the topmost, and the gripper must be free, otherwise you cannot take that. So these are all the preconditions. And then what happens? Well, the gripper isn't free anymore. We are holding A. It's not true that A is on B anymore. And it's also not true that A is topmost anymore, but instead B is topmost. What we see here now is the initial state and the goal description of the problem, which we have just extended. And so at the top, you see the graphical representation with, on the left, the initial state, and on the right, the state that we would like to achieve. And at the bottom, you see the domain representation thereof, the formal problem representation in PDDL. And this here is the file in which you can find that. But first, you can double check for yourself whether the picture on the top is actually adequately represented by the problem that you see at the bottom. I give you 30 seconds for verifying that, whether or not that's correct. I will do the same thing to stall a bit of time. And assuming that you're much quicker than me, I can say that the answer to this question is actually no, because the gripper is missing. And in fact, when I modeled this problem some time ago, I spent more than 30 minutes to find out about this. It was really annoying. Because if the gripper is not empty in the beginning. So if you forget to write that down in the initial states, then you will never be able to execute any action. And it just took me ages until I found that out. Although there might have been, I don't know, some ways to find out about this quicker. But yeah, that just shows how important it is to provide good modeling assistance in order to discover such modeling flaws. And yeah, if you open this this problem file here, then you will also see the missing state variable that the gripper is empty initially. Okay, anyway, if you go back to the domain model, then you will actually see that there were still tons of actions. So to recall, you were always assuming that, for example, you have A in the gripper already, and then created a model, like an action for putting it on top of B. But you also had that to put it on top of C, and so on for all the actions, for all the blocks that exist. So it's still quite a lot of work. Because of this, just for n blocks, we actually still have 40 actions, because as I've just explained, you would start with block A, and then you would put it on all the other blocks. It's n times n minus 2. And you have that twice, because you have that both for the stack and the unstack actions. And so you really do not want to model 40 actions for all this. And the number of state variables is 36, just for 5 blocks. So still quite a high number. It's still much better than modeling the entire state transition function, which would actually be higher than 501. To recall why I say higher, because in the table you might recall that it was actually exactly 501. That's the case because this model works slightly differently. In the original model, in which I've explained the state transition function, the gripper was taking a block and instantaneously putting it either on another block or on the table. But in this model here, we are taking a block into the gripper. That means we have more states. Yeah, and since this here is still too much, you do not want to model such a problem. There's a thing called lifted planning models, in which you basically just use variables instead of a fully so-called ground or propositional representation as the one that I've just shown you before. So we take again a look at the very same problem. So the actions still work in exactly the same way, but where we had state variables previously, we now use predicates. And predicates kind of work in exactly the same way, only that there are variables, here this B for a block B, and this can be then instantiated by any of the concrete objects, like all the blocks that we have, A, B, C, D. And yeah, the first variable is still the same as before, topmost, only that previously we had 5 distinct ones, and now we only have a single one, which says that yeah, the respective block that you put in is actually the topmost one. Then we have also on, like A is on B, so you would just again instantiate just the variable B and the variable B prime with respective blocks. We have on table again. It's basically exactly the same as we had before, only that now we use variables where before we have explicitly listed separate state variables. And in the problem instance, i.e. the thing that you have seen before, where I at some point forgot to specify that the gripper is initially empty or free in that terminology, you would also list all the existent objects. Okay, and oh, actually, let me show you this. So before we continue, I will show you how this looks. So this here is the planning domain, but I wanted to show you the problem instance. And so here in this problem instance, you see that in line number 5, we list all the existing objects in the A, B, C, D, E, and with a horizontal dash, and then behind this block, we state that all these objects, they are blocks. And then in the initial state, well, as before, you just specify the initial situation. So it still looks very similar to how we've done it in the propositional setting. Yeah, okay, now let's go back and let's do the final modeling exercise. So you will now again model the same action as you have just done, only that now you do it in this lifted setting where we have variables. So now you assume that you want to take a block B into the gripper, and you also assume that's an unstack action. So you don't take the block B from the table, but you take the block B from another block. So B will be on another block, which I have called here B prime, which can still be any block, right? It could be A, B, C, D, E. You don't know that. It could be any block. And oh, I've never noticed this. This here should be question mark B. And so yeah, in order to do this, you again go into the editor, and now you load the lifted domain model in there. So if you, let me see, there it is. So in this here, you select file, load, and then load the lifted domain. And here, I'm just assuming that at some point you will pause the video and do the exercise by yourself, or just say a few more words. So I'm assuming that you're checking out the syntax by yourself because it's pretty much self-explanatory. So at the top, we define types like block. There could be other types like truck or crane, crate, or whatever. Here we just have blocks. And in the predicates, we define of which type a certain variable is. Like here we have topmost, on, and so on, and all the variables that they use, they're all blocks. And gripper free, you see, doesn't need any variable because it's still a propositional variable. And if you, oh, how do I do that? I'm not sure how to scroll down here. Okay, that's weird. I'm pretty sure I did this successfully yesterday. Okay, wait, I can use my keyboard. So if you scroll down, you will see the exercise 3, and that is exactly that action that you should complete. And I'm assuming that you can recognize how the syntax works by looking at the other actions. So we can pause the video here, complete it, and then I will continue. And you should really do that so that you can see how a planner actually solves the problem, which will not be able unless you complete the exercise. So please try this. Okay, as said, I'm assuming you paused the video and did this. So I will just show the solution now. So the solution is that you need two parameters. They're both blocks, clearly, right? There are only blocks. And the precondition, well, if you put the other action, the grounder next to it, you will see it's exactly the same, only that now we use variables. So the gripper has to be free, one block has to be on top of the other. I'm assuming you can go through this by yourself. I think it should make sense to you, even if I'm not going through every single predicate here. In case you didn't do that yet, put this into the model now, because then you can actually solve it. So what you can do now is to load the problem instance, where you will get the same problem as before. Let me show you again. Yeah, so this is the problem instance that you will have to load. And after you have done that, I sadly cannot demonstrate this because I didn't fill this out, but you will be able to. And then you hit the solve button. You select your domains. Make sure that it's the lifted one, not the ground one, because the ground one is very incomplete. Then hit the plan button, and then you will get an output. In this case, you will get an error because it complains about wrong syntax. In my case, that's not a surprise because all these dots don't make any sense. In your case, it should hopefully not complain about any problem. But if it does, then you know that you have done something wrong. And once you completed that successfully and correctly, you will see the plan, which will be the following. So it will first unstack A from B, then place it on the table, to this, to that, and so on. So you can just verify that this sequence of actions is actually doing the right job. It will actually transform the left state into the right one. I think that's pretty cool because, well, it's autonomous planning, right? It's not a dedicated blocks world solver or anything. It's just a general problem solver, or it's not that general, it just solves planning problems, obviously. But you can define any planning problem that you want, it's solving it for you. So yeah, that, by the way, completes the all the practical part. So now I'm only concluding with a few final remarks. We are now looking at the size that this new model has, because I wanted to make the point that using such a lifted planning model is much, much smaller than exploring the entire search space that you could possibly produce. In the propositional model, we still needed n squared many actions and state variables, but now in the lifted model, we only need 4 actions and 5 predicates. That's constant, right? Even for bigger blocks world problems, whether you have 10 blocks, 5 or 50, it doesn't matter. This will always stay the same. It will always be 4 actions and 5 predicates. Only the number of blocks scales. So there will be, you will have to list as many blocks as you have. I can go back and illustrate this. So that's basically line 5. You have to list the blocks, although you will still have to model the initial state in the goal description. So in lines 7 and following and 12 and following, you will of course still have to specify the current state and the desired state by means of all the blocks that you have. But you can never prevent that because it's an integral part of your problem description. Yeah, that means that every single blocks of problem can be modeled with just such a minor number of, yeah, let's say content or lines of code. So to conclude the entire lecture, you have learned the foundations of classical planning, including the formal problem definition. You got to know PDDL, and you should be able to model other problems now as well. You have basically understood the main concepts of the syntax. And you played around with the editor that's available on planning.domains, or more precisely, it's editor.planning.domains. There's other content on there. And you have modeled problems there and also won a solver, hopefully. I didn't do that. Actually, I did. It just failed because I didn't use a completed model. Okay, also a quick outlook. As said, we have only dealt with classical planning, but there are many extensions. So, for example, you could introduce uncertainty into the model, that that actions, for example, might have multiple outcomes, like rolling a dice, and you don't know which one. There could be partial observability, that you don't see everything, and there might be sensing actions, like in this imaging chamber of the conveyor belt domain, like the greenhouse domain. There could be resource consumption and production, that actions actually put some other objects into existence or consume objects. You could have state trajectory constraints. What I mean by that is, let's say that this is our state of, no, our sequence of states. So there are always some actions in between. And so far, we were only specifying actions, but you could do such a thing as specifying that from a certain state until another state, a certain property has to hold, like a door of a truck has to be closed or whatever. And you can define hierarchies on actions. That's my research area. And yeah, these are just extensions to the problem setting, like to the kind of problems that you're being able to express. And now the rest shows what kind of research you could do. So there's research in how to solve these problems quickly, because you were lucky that the solution was solved or found pretty much instantly, but the bigger the problem becomes, the harder it is to solve them, and you still want to obtain a problem quickly and don't want to wait for hours and hours. And if you think it's unrealistic that you have to wait for hours, then please think about again how large the state transition function is. With like 18 blocks, right? That's an insane amount of states that you would have to search through in the worst case. So you really need to have efficient search algorithms here. And yeah, that's a main research area, both of mine and in general. You can do complexity analysis, so you can search for, you can investigate how hard it is to solve a problem computationally. And as I said in the very beginning of the talk, there are other questions that you might investigate. For example, how to prove unsolvability of a problem, how to provide explanations, how to explain unsolvability, like giving a reason why a problem is unsolvable, or You can support a domain modeler like all of you or like me in putting together a model and give valuable advice, so such that somebody like me doesn't have to spend 30 minutes just to realize that he has forgotten a predicate in the initial state and just say right away, hey, no single action is executable. There are a few possible reasons. Yeah, that concludes the lecture, and thank you very much for listening.